The formula for the cross-section for E plus E minus to mu plus mu minus in quantum electrodynamics. The answer is written up here at the top of the blackboard. Now, it would seem like we have a lot to do in this. Oh, that's cool. We have a lot to do in this course, and there's no time to do things twice or three times over. But I guess the next thing I wanted to do is to rederive this result in another way. The purpose of this is to introduce some other ideas and formalism which we're going to try and make use of throughout the course. So the main idea that I'd like to get you used to in this lecture is the idea of what are called helicity amplitudes. That is, the use of a term I'll define in a moment, helicity, as a kind of key to prying apart the physics in elementary particle interactions. So what is helicity? Let's say you have a particle that's moving in a certain direction, and it also has a spin. So it has some momentum, and it has a spin attached to it. The helicity is the spin quantized along the direction of the momentum. For a spin-a-half object, this is really easy. A spin-a-half object either has spin up or down along some axis. And in fact, if it's spin-a-half, it's either pointing that way or that way along the axis. So we can have a spin which is helicity plus a half or helicity minus a half. And we would also call these a right and a left-handed particle. A right-handed particle or a left-handed particle. Helicity has some basic properties. If I go from the particle to the antiparticle, so I ask, if I have a field that destroys this guy, what particle does it create? The thing it creates has just the opposite angular momentum to what it destroys. And so what it will create is a left-handed particle, and this one a right-handed particle. Helicity is odd under parity. And so if you have a parity invariant theory, like the electromagnetic interactions or the strong interactions, parity will interchange these two states. Helicity is pretty useful in general. And actually, at the very end of the course, I'll apply helicity to the analysis of the top quark decaying to a W boson. So that's a massive particle decaying to another massive particle, plus a bottom quark. But it's most useful when you think about helicity for massless particles, because a massless particle always moves at the speed of light. And so whatever you do to it, however you rotate it or even boost it, it's always still moving at the speed of light. For a massless particle, the helicity is a well-defined Lorentz invariant quantum number. You can't make a Lorentz transformation that, well, maybe I should just show you one thing. If I have a massive particle, and I start out that massive particle in a right-handed spin orientation, if it's massive, I could always bring it to its rest frame, and then I could run a little faster, and I could watch it go the other way. And now I've turned it into a left-handed particle. But for a massless particle, you can't do that. You can never bring it to its rest frame. And in fact, Lorentz transformations always preserve the helicity. So as long as we can ignore all the masses in the problem, helicity is a good quantum number, which is extremely useful. And so what I'd like to do now is to work out this same cross-section again in a helicity basis. And I hope to illustrate through that the use of this basis makes the physics just really transparent. And this is an idea that's going to come up again and again in the course. So it's probably good to get used to it right at the very beginning. So what I'd like to do now is to go back to this process, compute the Feynman diagrams in a way that probably you're not so familiar with, which is to, instead of summing over spinors and using trace techniques, I'd like to actually write the explicit spinors and manipulate them. And in the end, we'll come back to this answer, but I think we'll understand what's in that answer a lot better. So once again, we start with this Feynman diagram. And the value of that Feynman diagram, as I wrote down last time, now let me just write 1 over S here. S, remember, is the invariant square of the momentum going in this channel, and it evaluates to the square of the center of mass energy. U bar gamma mu V for the final state muons, V bar gamma mu U for the initial state electrons. So now what I'd like to do is to consider all the various helicity configurations that are possible in this process and just explicitly work out this amplitude for all the cases. So the first thing we need are the explicit forms of these spinors. And maybe I should just say this is easiest to do when everything is moving along the 3-axis, because then things will be diagonalized. So I'd like to analyze this process in a frame where the muons are moving along the 3-axis and the electrons, oh, maybe I should have drawn it the other way. The electrons are moving along some other axis which is rotated by an angle of theta. What I'd like to do first is to just write the Dirac spinors for these muons, and that'll be most straightforward if we choose this basis for the gamma matrix, the chiral basis. So sigma mu is 1 sigma, and sigma bar mu is 1 minus sigma. So then the Dirac equation, P slash minus m equals 0, K slash minus m equals 0, I can write out like this, as minus m is diagonal, K 0, the energy of the particle, appears up here. Here I have a sigma, but it's a Lorentz dot product, so it's minus K dot sigma. Actually, this is K sigma 3 if it's moving in the 3 direction, and E plus K sigma 3 there, and that acts on U. And so then you can pretty easily find the eigenstates of this matrix. They have the following form. U is equal to, if I have sigma 3 is equal to plus 1, U is a 4-component object made of two 2-component objects. So if I write this, I have that sigma 3 equal to plus 1. And then you can see if you write the square root of E plus K down here, that is an eigenstate of this matrix. And the other possibility is sigma 3 equals minus 1. Then if I write the square root of E plus K here and the square root of E minus K here, I think I'll get another eigenstate. Now, if you like, I could also write this as the square root of E minus K, the square root of E plus K, times 1, 0. This thing actually is the is the spinor of the fermion that I'm describing. And this is a spinor which is up along the 3-axis. So this is the helicity equals plus a half, or right-handed muon. this one over here is the helicity equals -1/2, or left-handed Mueller. Okay, one very important thing to note is that if I set the mass equal to 0, this whole part of the spinner goes away. And I only deal with a two-component spinner now. Similarly, if I set the mass here equal to 0, the bottom half of the spinner goes away, and I only deal with a two-component spinner. And this is the thing that I told you in the first lecture. If you set the mass in the Dirac equation equal to 0, it splits into two-component equations, the Weyl equations. And two-component equations are just simpler than four-component equations. So if we can take advantage of that, we should. I'll take more advantage of that in a later lecture. I think I'm going to follow the math through so that we get this whole formula. We also need the spinners for antiparticles. So those are the solutions to the equation k/+m on V is equal to 0. Here, let me compactify this a little. For V, the corresponding solutions are the following. If I take an up spinner, actually, let me just write it in this way. Maybe that's simpler. If I put a minus sign here, that would compensate the change in the minus sign to a plus sign in this equation. And now I have the V spinners for particles that are moving in the 3 direction. Now you have to be a little careful. The spin in the V is the opposite of the spin of the fermion. So this is actually the minus case, and this is the plus case for the antiparticle. And now I'd like to do one more thing, just to confuse you totally, which is that if you look at this picture over here, the antiparticle is going in the -3 direction. So this is for P parallel to the +3 direction. If I want P parallel to the -3 direction, I have to rotate this guy by 180 degrees. And rotating that, the rotation just acts on the spinner. And so if I have the P parallel to the -3 direction, that would be this structure. E plus K 0, 1 for the helicity equals -1 spinner, and E plus K, E minus K with a minus sign, and -1, 0 for the helicity plus a half spinner. Okay. So now we've got all the equipment that we need. And now what we have to do is basically just work out the the matrix elements that are apparent in this equation. So let me do that. Electrodynamics is really simple because it's a current-current interaction. So we can analyze this problem by just looking at the current here and trying to evaluate that explicitly for all the different Felicity configurations. And let me just do that. So what I want to do is to calculate U bar gamma mu v with various combinations of the u's and v's that are written in this line and in this line. So U bar gamma mu v is U dagger gamma 0, and then it'll be 1, please excuse me, sigma mu, sigma bar mu v. So it'll be U bar sigma, please excuse me. I'd like to break these into the upper and lower components. Oh. Sure, excuse me. Is that better? Okay. So if I write U as UL, UR, and V as VL, VR, please notice that UL is the part that hangs around if I go to 0 mass for a left-handed particle, and UR is the part that hangs around if I go to 0 mass for a right-handed particle. So this now takes the form gamma 0 in this basis is that. So this will be UL sigma bar mu VL plus UR sigma mu VR. Okay. And then we can compute all those things. So let's try this and see how it goes. If I have this guy being plus and this guy being, if I have this guy being minus and this guy being plus, then what we get is the following. So we'll start up there. The square root of E plus K. What's here is 1 minus sigma. I need the spinner, which is 0, 1. I then have 1 minus sigma. And then the V equals plus is this one here. That gives another factor of E plus K. And minus 1, 0. Yeah, that's right. So all in now plus the right-handed parts of the spinner. So this thing here, 1 sigma, and again 0, 1. From here, the right-handed part of the spinner, which has a minus sign, and minus 1, 0. Okay, I think I've got all the pieces there. In the limit of 0 mass, only this first term would contribute. And what I would get is E plus K, or in the limit of 0 mass, 2E. The one term doesn't contribute, please notice. This is the matrix element between here and here has to be off diagonal. The x component is 1. The y component is, this matrix for the y component has a minus I down here. So it's 1. Did I get that right? 1 yeah, 1I. And then the third component, it's diagonal, and this is off diagonal, so this is 0. And for this term, actually, this minus sign, there are two minus signs here, there are two minus signs here. It's the same story. So we get E minus K times the same thing. OK. So the final result for this particular matrix element is 2E times 0, 1I, 0. Well, now you can immediately see that that's exactly the right answer. Because what is this vector here? That vector is the angular momentum vector for spin 1. And maybe I can write it a little more explicitly as 2E times 0, there's an extra factor of the square root of 2, epsilon minus star, where epsilon minus is 1 minus I, 0. It's the polarization vector for something with negative minus 1 unit of angular momentum. And so from this calculation, you can see exactly what's going on here. What's being produced is this state that I showed you before with a muon that's left-handed, so it has angular momentum that way in half a unit, together with a right-handed mu plus, which has angular momentum that way. The whole system then has J3 equals minus 1 and J equals 1. So the angular momentum of such an object is described by this vector. Because it's in the final state, there's a complex conjugation, and that gives exactly what we got. OK. Well, that's really pretty nice. What about the other matrix elements? Well, now we can just try and compute them in the same way. Yes?
Sorry, could you explain again, when, at the beginning when you started to calculate this matrix element, you have the minuses and the pluses on the little arrows, and then you had pluses written on your squares.
Right. OK.
Can you just explain?
OK. So once again, this is the helicity of the particle. So I'm going to first do the computation for this state where I have a left-handed mu minus and a right-handed mu plus. Okay? And so then what I did was I took this guy, I broke it into two component things. And that's just multiplying out these matrices. Then the UL and the UR I'm going to take from the components of the spinors that I've written out here explicitly. So I'm interested in the negative helicity spinor. So this is the UL. That times that is the UL. And this times that is the UR. Okay? And sorry? Oh, sorry. That's a dagger. Okay. If you want, I can write transpose. If it were complex, it would be a dagger. Okay. Then this gives this. On the other side, I've got VL. So I've got VL. It's this VL here. So that gives this. And then you just multiply out the matrices. And you get this. Here, we work with the right-handed pieces. So this piece and this piece. And it gives the same thing, except E minus K instead of E plus K. And then everything adds together neatly. And there it is. It's exactly the expression of the angular momentum flow into the current. Got it. OK. So, well, this stuff is all in the notes. So maybe I should just quote the answers for the remaining cases. So let me, sorry? I haven't, no, I finished writing it down. Oh, I'm sorry. Okay. So maybe I'll carve off a little space here and write down this matrix element. So I am, sorry, the U bar gamma mu V for a left-handed mu minus and a right-handed mu plus is equal to what I wrote here, 2e times the square root of 2 times 0 epsilon minus star. And I think it will be fairly obvious to you that this should work, and it actually does work, that if I take a right-handed mu minus and a left-handed mu plus, and I use this matrix element and this matrix element, I'm going to get exactly the same thing, except that because this spin is down and this spin is up, I'm going to interchange the two components of sigma 2, and that's going to flip this I to a minus I, and then I'll get exactly epsilon plus. So this has J3. This is producing J3 equals minus 1. This is producing J3 equals plus 1. Now there are only two more matrix elements. Yes? Oh, well, the first thing I derived was this. So that's totally straightforward, except for the fact that the spin in the spinner in the antiparticle is the opposite of the spin of the actual antiparticle. Okay? And, well, there are several ways to think about it. One way is you just write down the spin operator for the Dirac equation, and that minus sign appears. But a better way to think about it is that the antiparticle is a whole. Okay? So the V, the thing that creates the particle, annihilates the antiparticle. So the antiparticle is like a hole in the Dirac sea. And if the particle in that hole has a certain spin, the hole has the opposite spin. Okay. So this thing, which looks like a spin down, is actually the spin up spinner of the antiparticle, or the spinner of the spin up antiparticle.
So shouldn't we also get the minus sign?
Sorry?
The plus 1 LS3 and the minus 1.
No, this is spin up, and this is spin down. Yes?
There we have the minus 1.
Oh, no. Then I did something else. I haven't explained that to you yet. Or rather, I did explain it, but I'll explain it again. So this is for an antiparticle moving in the 3 direction. Now, in that diagram, the antiparticle is moving in the minus 3 direction, which means I have to take the spinner and rotate it by 180 degrees. Okay? If you do that, this guy rotates into that guy, but this guy rotates into that guy with a minus sign, because that's the way spin half works. Okay, when you rotate by 360 degrees, you get a minus sign. So it's actually all right. Okay. Good. So now there's only one other calculation that we have to do here, which is what if I had both pluses or both minus? Let's do both minus. Maybe that's easier. You guys all have the notes, so I'm going to be a little cavalier and just start erasing things. This line is still correct. We have to change this spinner now. So here I want the minus Felicity spinner. I want this guy. So the upper component is the square root of E minus K times 0, 1. And with a, yeah, that's right. And then here I get the square root of E plus K with a 0, 1, and with a minus sign. Okay, well now look what happens. Now I need diagonal matrices to make that bridge. So I'm going to get, in this line, E minus K times E plus K is E squared minus K squared, the square root. The matrix elements are 1 0, 0, 1 minus square root of e squared minus k squared, 1, 0, 0, minus 1. Okay, very good. And so in the end, what we get is, this is the mass of the particle, 2m 0, 0, 0, 1 mu. Or u bar gamma mu v for a right-handed, I guess I did a left-handed mu minus and a left-handed mu plus, gives 2m times the polarization vector in the 3 direction. And so that's, again, exactly what you expect. If you have this guy having angular momentum j equals minus a half, and this guy, it's also negative helicity. The angular momentum points that way. The total J3 equals 0. And so you should get the vector for J3 equals 0, and that's what we got. OK. A very important property of this amplitude is that instead of being proportional, oh, sorry. You guys have a question. Why don't you ask me?
Sorry, what does a J mean?
Oh, J is angular momentum.
Okay.
I'm sorry. OK. A very important property of this amplitude is that it's proportional to the mass rather than the energy. So if I think about a very high energy limit, this amplitude is going to be totally unimportant with respect to the others. So in the high energy limit, you only produce the left-handed muon with the right-handed anti-muon, or vice versa. In fact, that makes perfect sense in relation to what I said in the first lecture. When the mass goes to 0 or is negligible, the Dirac equation splits into two pieces that don't talk to each other, one involving the left-handed fermion, one involving the right-handed fermion. So naturally, if you try and produce particles with a current, you're always going to produce the particle and the antiparticle. The particle, the muon, has the left-handed muon has its antiparticle, the right-handed muon. And that's the only important amplitude in the massless limit. The right-handed muon has as its antiparticle the left-handed anti-muon. And that's, again, the only important amplitude. And this thing is important for low energy, but it becomes totally negligible at high energy. And when we go over to thinking about really high energy processes, what I'm going to do is basically just ignore this line. And that'll be a very good approximation. Ignoring that line has some specific implications about the angular momentum, which I'm now going to make even more explicit. OK. So those are the current matrix elements. Now what I have to do is to put together the two current matrix elements to make this full scattering matrix element. So can I now erase the blackboard? Are there any serious objections? Once again, you'll find all these formulae in the notes. So OK. Now, for the electron in the initial state, what you see is this guy is just the complex conjugate of those matrix elements. The electrons, remember, are coming in a different direction. They're coming in a direction rotated by theta. But I think it's easy to deal with that. We just have to take the explicit vectors that are in these answers and rotate them by theta. So if we do that, we can compute, for example, the matrix element for a left-handed electron to make a left-handed muon. It's I e squared over s. This matrix element for the muons is the one that I've written here. 2e times the square root of 2, or maybe I should just write this out explicitly, 0, 1, I, 0. For the electrons, I'm going to get the same thing, 2e, and then it's not complex conjugated, but what it is rotated by an angle theta. So there'll be something like sine theta minus I cosine theta, sorry, cosine theta here and sine theta here. So what I did was I just took that vector and I rotated it by theta. Okay, now we can take the Lorentz dot product of these two guys. I times minus I gives 1. 1 times cosine theta gives cosine theta, so we get 1 plus cosine theta. So if you now work hard and get all the factors right, there's a 2e, a 2e, and this guy is 4e squared. And so everything very neatly cancels out, and what we get is I e squared times 1 plus cosine theta. Oh, I'm sorry. I forgot one thing. The Lorentz dot product has a minus sign, so there's a minus sign. Okay, now what if I consider the opposite case? I am E left, E plus right, going to right-handed muons. Okay, in that case, I just have to flip this sign. So that flips the sign in front of the 1, but not the cosine theta. So I'm going to get I e squared plus 1 minus cosine theta. And then there's one more case we should think about. Let's say mu left, where the two... Sorry? I'm sorry? From here to here?
Yeah.
Oh, sorry. What I meant to write was mu right, mu left. So I produce now the right-handed muon. And now I'm going to produce a left-handed muon and a left-handed anti-muon. So for that, I have to dot with this last vector here. So instead of an E, I'm going to get an M. So I'm going to get M over E. And I have to take the dot product of this vector with this vector now. So there's going to be a sine theta. And I think I'm not going to bother with the factors of 2, which are correct in the notes. Actually, this is really right, except for a minus sign. And then if I have mu right, I'm going to get the same thing. I forget whether there's a minus sign in front of it or not, but it's the same amplitude. Okay. Any of you guys familiar with d functions in angular momentum? D, J, M prime of theta. Anybody know what that is? So if you take a rotation matrix in spin J and you peel off the factors of e to the I phi, it's this. And these matrices here are exactly those d functions. This for rotating a spin 1, j equals minus 1. This for rotating a spin 1, minus 1 to minus 1 is this, minus 1 to 1 is this, and minus 1 to 0 is this. So the angular momentum dynamics is, again, completely exposed. And maybe I could just make that a little more explicit. If I have my left-handed electron coming in, and what goes out is a muon with some angular momentum, if it's a left-handed muon, then the amplitude is very large in the forward direction by angular momentum conservation. If it's a right-handed muon, the angular, So here, the angular momentum is kind of maximally aligned in the forward direction. So that's where the amplitude is large. Here, the angular momentum is maximally aligned if I turn the muon around into the backward direction. And that's where this amplitude is large. And if I have a state of angular momentum 0, it's not particularly large in either direction, so it's peaked in the middle. And so now if I just take the squares of these amplitudes, I should get the angular distribution. And so if we just take the sums of the squares of these amplitudes, we'll find the following thing, that d sigma d cosine theta is proportional to 1 plus cosine theta squared plus 1 minus cosine theta squared plus m squared over e squared sine squared theta. And then there's another one, which is mu right, so that's going to give a factor of 2 here. And if you just simplify this expression, you get 1 plus cosine squared theta plus m squared over e squared sine squared theta, which is exactly what we got in the previous lecture. But now we actually understand where it's coming from. If you have a left-handed electron beam, then as a function of cosine theta, so this is forward and backward, there's a distribution like this, which is producing left-handed polarized muons, a distribution like this, the square of that, which is producing right-handed polarized muons, and something in the middle, which, by the way, is extremely small when the muons get very relativistic, which is producing the Felicity 0 case. OK? So at this point, I think we not only have this formula, and we can compare it to experiment, but we have a, well, more or less complete physical understanding of what's going on. OK, are there any questions about this? Now, in view of the thing that I told you in at the end of the last lecture, I'd like to make one more comment about these formulae. And that is that these formulae, or at least these, let me not do this in full generality. Let's now take the zero mass limit of these formulae. I've already ignored the mass of the electron, but now I'm going to also ignore the mass of the muon. Then this one becomes 0. This one becomes just what's written, I e squared 1 plus cosine theta. And this one becomes I e squared 1 minus cosine theta. Now, I'd like you to think a little about the kinematics of this process. If I have these three invariants, S, T, and U. S is 4e squared. T is the square of P minus K. So if you work that out, that'll be minus 2e squared, 1 minus cosine theta. And U, if you work it out, is minus 2e squared, 1 plus cosine theta. So these expressions are also extremely simple in terms of the Mandelstam variables in the problem. This one is exactly 2e squared u over s. And this one is exactly 2e squared minus I times t over s. And now we're all set. We can use these in any channel. If I want to compute not electron positron going to mu plus mu minus, but electron muon scattering, I would just flip the diagram over. The calculations are all exactly the same. And then what I would do is just evaluate this with some interchange of the variables u, t, and s. And in tomorrow's lecture, we'll make strong use of that to do some calculation. So we've done a lot of hard work in quantum electrodynamics today, but we've actually made a lot of progress. And we've generated some very simple formulae which are actually quite useful in many ways. And we've also, I hope, got a complete physical understanding of the physics that's in this cross-section formula. Yes?
The formula that we get last lecture, we average over the initial
Oh, you're absolutely right.
In this case, you are with a fixed.
In this case, we're with a fixed initial spin. But electrodynamics is parity invariant. So if I have the initial right-handed electron, it annihilates a left-handed positron. It makes a forward right-handed muon and a backward left-handed muon. So all the formulae are just copied with parity interchanges of all the helicities. Okay? So I had this diagram before. Actually, this will be quite important later, so maybe it's good to make the point explicitly. If I have a left-handed electron beam, then I have these three components that I drew for you, where this is the left-handed muon, this is the right-handed muon, and this is the left-left and right-right, the so-called helicity violating. Now, if I change the electron beam momentum, from there to there, it's parity. And electrodynamics is parity invariant. So you get exactly the same diagram, except that now these are the right-handed muons going forward, and these are the left-handed muons going backward. The cross-section formulae are the same, and so then you get this same expression, and then to get the prefactor right, you should do that averaging correctly. And maybe I should just say there are 4 cases that you average, but 2 of them don't do anything. If I ignore the mass of the electron, a left-handed electron can never annihilate on a left-handed positron because those particles are not particle and antiparticle. So what I'll have to do is to add this, and add 2 0 cases. And if I get all the numbers right, I'll get the correct prefactor. Okay? And I encourage you to do that exercise. Yes?
So on this calculation, you can actually figure out what happens if you collide with polarized species.
Absolutely.
Is it easy to polarize species with electrons?
No. But we'll talk about that in the last week of the course. The experiment's been done. And not only do you get the right answer, but it's extremely enlightening about the weak interactions. So in the 3rd week of the course, I'll tell you what happens when you include the weak interactions and you use polarized beams. But maybe I should make one more comment about that. If you want to study left-handed top quarks, and you had a very high energy E plus E minus collider, you could do that in the following way. You could create a left-handed electron beam, collide it with a positron beam. The positron beam doesn't have to be polarized, right? Only one beam has to be polarized to get the effect. The forward guys are left-handed top quarks. And so then you can study the specific properties of the left-handed top quarks by looking at this angular region. Actually, at the Z, this is done with bottom quarks. And so we know that the polarized bottom quark decays preferentially into a polarized lambda particle by doing experiments. Okay. So now, let me just write one more formula before we go on. If you take this formula and you integrate that formula, you can get a formula for the total cross-section. And it's worth writing that down. If I just take that formula and integrate over cosine theta, I'm going to get the following result. D sigma now is equal to, there's a pi alpha squared over S, the center of mass energy squared, let's see, if I integrate 1 plus cosine squared theta, I'm going to get an 8/3 pi. So there's a 4/3 that comes out in front of that formula. And then there's some specific mass dependence that comes from the formula, which turns out to be 1 plus 1/2 m squared over e squared, and then the k over e, which is 1 minus m squared over e squared to the 1/2. So that's the formula for the total cross-section. It's a kind of interesting formula, because if you plot it versus the center of mass energy, phase space is just this, and that rises rather slowly. This factor is largest for small values of the energy, and so it's a faster rise than phase space. And if you actually compare this to the data, this formula actually works better. I think in the slides, there's some data on the threshold for the production of the tau lepton. And you can see, I think this is page 2 of the PDF figures for this lecture. You can see that there's a characteristic shape for each spin. So this is the characteristic shape for spin 1/2. The characteristic shape for spin 0 in E plus E minus is very low. And the characteristic shape for spin 1 or 2 will rise a little faster. So you can actually measure the spin of a new particle by looking at the shape of its threshold. And in particular, this formula fits very well the production of the tau lepton, which I claimed was a spin 1/2 particle exactly like the muon and the electron, but heavier. This is part of the evidence for that. Yes?
Sorry, what's the difference between the first two?
So this curve here is only this factor, and the top curve adds this factor. Yes?
The previous diagrams you gave, were they on the dependent axis theta or cos theta?
Cosine theta. So you can write it as a function of theta, but it's a simple function of cos theta. OK. So now, finally, what I'd like to do is to tell you something about quarks. Now, there's only 5 minutes left in the lecture, but what I want to tell you about quarks is actually very simple. Let's say that, as I told you, but I didn't try to prove it yet, quarks are elementary spin 1/2 particles. Oh, sorry. Let me. Sorry. Yes.
Why is the graph growing with growing energy if you have a negative power?
Here.
It's 1 over E. So why is it growing?
Well, E can never be less than M. So this is going to be 0 at threshold. Okay. And so what's going to happen, eventually all these things roll over like this. Okay. Due to the 1 over 4 E squared that's in here. But the very near threshold behavior is different.
But isn't it growing? I mean, if you have 1 over E, then it should die, it should decay, not grow. Why is it growing at the threshold?
Oh, well, sorry. This is 0 at threshold. And if I go above threshold, if E is less than M, it turns positive. So it should grow, and then it should decay. Okay. Let's see. Let's just take the limit when M is much less than E. So then this turns into this number 4/3 alpha over 3s. And this is some definite QED result that we can compare. OK, now let's talk about quarks. Now, I told you that quarks were elementary spin 1/2 objects. I told you that they had these funny charges of 2/3 and minus 1/3. And of course, you know that quarks have strong interactions. So the first thing I'd like you to think about is, what if quarks didn't have strong interactions. Then we could produce quarks in E plus E minus annihilation the same way that we produce muons in E plus E minus annihilation. We would just annihilate an electron and a positron. We would make quarks. The formulae are actually almost identical to the ones that we've described. I mean, here's the Feynman diagram. You take an electron, annihilate it with a positron. You have a virtual photon here. And then you make a quark and an antiquark instead of making a muon. What's the difference between this diagram and the previous one? Well, the matrix element is just what we did previously. And then there are some corrections that we have to make. First of all, the quark charge here is different. So we have to multiply by the charge of the quark, which would be 2/3 or minus 1/3. Secondly, we should take account of the different masses of the quarks. But to just make it easy, I'm going to just assume we're at such high energy that the quarks can all be treated as massless. And thirdly, quarks have this funny color quantum number. So we have to take that into account. So now, let me write some predictions that follow from this picture. That, first of all, the d sigma d cosine theta for electron-positron going to quarks should be exactly the same as the muon one at high energy, namely 1 plus cosine squared theta. Secondly, the cross-section for E plus E minus to QQ bar should be exactly the same as the muon one, namely 4 pi alpha squared over 3s, times some extra factors that follow from these modifications. Namely, we have to put the square of the quark charge here. And if quarks come in 3 colors, we probably better multiply by 3, because you can produce a pair of red quarks, a pair of blue quarks, or a pair of green quarks. And finally, if we can't tell the quarks apart, we'd better sum over them. OK, now what actually happens in experiment? Well, it's interesting to think about the high energy first. So in the last lecture, I showed you some pictures of high energy reactions that involve E plus E minus to QQ bar. I said QQ bar. And what those reactions looked like were reactions where you had a whole mess of tracks going out roughly in 2 different directions, maybe some extra guys over here. But there was a directionality to the alignment of the tracks in the event. And they were very complicated events. But we can ask 2 questions about those. First of all, is the total cross-section right? And secondly, what about this alignment? Well, the interesting thing is that if you, by some measure, try and associate an axis with the event, let's say that axis which minimizes the amount of momentum transverse to that axis, and then you look at the orientation of that axis, well, I think I have the angular distribution in one of the pictures. So this will be, if you go to page 2, page 3 is a picture of a typical event from SLD. So you can see exactly what I mean by this orientation of tracks. If you go to the next page, I have the angular distribution that was measured by the Olive experiment at LEP at 91 GeV. And wow, it's 1 plus cosine squared theta. And the other thing is the value of the cross-section. So let me now evaluate this quantity. So if I'm at very low energy, maybe I should only consider the up, down, and strange quarks. So probably about 2 GeV. The up, down, and strange quarks are very light, and I can ignore their masses. And the charm quark, which has a mass of about a GeV, hasn't come into play yet. And then the value of this quantity is 2/3 squared plus minus 1/3 squared plus minus 1/3 squared, which is equal to, if you work it out, 2. If I add the charm quark, then I get another 4/3. That is to say, the square of a factor like that. If the bottom quark comes in, I get another factor 1/3. And so the claim is then that if I plot the cross-section for this process versus the cross-section for mu plus mu minus production as a function of energy, that cross-section should be roughly flat. That ratio, rather, should be roughly flat with these particular values. 2, and then somehow the charm quark will come in, and there'll be a step to 3 1/3. And then somewhere the bottom quark will come in, and there'll be a step, and it'll go up to about 3 2/3. And then in the next picture, you see what the data looks like. Now, if you ignore the regions that are hashed out here, you'll see that the data looks exactly like that. This ratio is flat over large regions of energy, and the values that those correspond to are actually quite close to these values. It's not exactly right because, well, we shouldn't expect it to be right. We totally left out the strong interactions. But nevertheless, the picture is correct. You produce the QQ bars by annihilation. We can compute the cross-section from quantum electrodynamics, and within 10% we get the right answer. Sorry? Oh, we haven't gotten there in E plus E minus yet, so there's no data. The top quark threshold would be at 350 GeV. So we don't have an E plus E minus collider that powerful yet, despite my best efforts, I should say. Yes?
Did you say that you approximated the electron mass or the quark mass to be 0?
Both. Here. Both. OK, now what happens in these intermediate regions? Well, that's actually kind of interesting to think about. If I have let's say, the charmed quark, and I make the charmed quark in E plus E minus, one of the things that I should be able to make are the bound states of the charmed quark. So I should make bound states, which are bound states of CC bar. They're produced from a point, so they should be orbital S states, that is L equals 0. The initial electron beam, as we've seen, is spin 1, so they should be J equals 1. That means they have to be spin 1. There should be actually a sequence of those states, and they should have other properties that would tell us some of the key features of quantum mechanical bound states. And in fact, if you look and see what's in this region, it turns out to be exactly true. If you plot the E plus E minus to hadrons cross-section in that region, there's a huge resonance at 3.1 GeV, which is called the J psi particle. There's another at 3.7 GeV, which would correspond to the 2s state in that system. Much more complicated behavior up here. And then eventually, this ratio that I've talked about here settles down to the value very close to 3 1/3. The same thing happens in this region, where there are 4 or 5 distinct states which would correspond to the first 4 or 5 S states of the BB bar system, called the upsilon resonances. At very low energy, it gets more complicated. This turns up here. There's some resonances called rho and A1. And then this cross-section, of course, has to go to 0 at the 2 pi n threshold. Down here, you can't ignore the strong interactions. But for some funny reason, there are large regions of this energy where, for the purpose of computing this cross-section, you can ignore the strong interactions. Somehow the strong interactions are not acting in conjunction with electrodynamics in the quark-antiquark production process. It's almost as if you produce the quarks and antiquarks. They're free particles at short distances. Then they go out some way. And then all of a sudden they say, oh my God, we're strongly interacting particles. And all kinds of crazy things happen. And then you produce all the particles that you saw in that event picture. But in such a way that the momentum flow in the process remembers the quark origin and has exactly the spin-a-half character for the angular distribution. Weird. But that's the way it is. So this actually turns out to be a clue to the nature of the strong interactions. And I'll have another rather similar clue that I'll discuss in the next lecture. Now, let me give one more word of orientation for those of you who are actually looking at the lecture notes. In the lecture notes, the next lecture is a lecture about these bound states. And the purpose of that lecture is to convince you that these bound states have many properties that are identical to the properties of quantum electrodynamics bound states, the hydrogen atom and positronium. In my lectures here, I'm going to skip over that lecture. But for those of you who are interested in the question of whether quarks are real, it's very interesting, and you might want to read it. But we're going to go right on to the next topic tomorrow. OK, you had a question.
Just to clarify, these resonances are heavier particles that are compounds of the quarks that are produced?
That's right. So if you think about what would happen if you produce some fermions, the first thing you'd see a hydrogenic system. So you'd see the 1s, 2s, 3s, 4s, 5s, etc. Then eventually you get to threshold. Then you'd see free fermion antifermion pairs. And then where it's flat, it's the production of free particles, which should be well described by the simple Feynman diagram approach. Of course, ignoring the strong interactions. We're still ignoring the strong interactions. Good. OK, that's it. See you tomorrow.
So just to clarify, there's going to be 2 tutorials this afternoon. If you guys match understand the model.